Hello again, simulation team. Welcome to the second static structural video in which we will solve another static structural problem. This time we will be looking at a very important part of any rocket, the engine. This problem will be longer than the first one because we'll be doing more things at each step of the simulation process. When the engine is fired, it produces thrust along the axial length of its casing, which propels the rocket up in the air. That thrust force has to pass through the casing to affect the rest of the rocket, and this is the phenomenon that we will be addressing in this simulation. Like the last time, we'll also be using a thermal condition to simulate the heat from the combustion, and a pressure to simulate the outward force from the combustion. The radial force, so to say. We need to find the reaction force along the length of the casing, and the equivalent stress and strain due to both the thrust, temperature, and pressure of the motor as it's fired. Let's get started. We'll launch Workbench and create a static structural simulation. Fun fact, Workbench 17.2 has come out since last week. Absolutely nothing has changed about the user interface, so you guys don't need to worry. We get this maximized, and we'll do a static structural. The material is steel, so we'll start with geometry like last time. Double-click to launch Design Modeler. The 2D sketch that we want to extrude for this casing is a circle with another circle inside of it. Select the ZX plane, click the New Sketch button, and then draw two circles centered at the origin. It's done via the Sketching tab, and circle, click at the origin, and click anywhere else. Repeat once, but put the second circle inside the first. Select the Units menu and then pick millimeters. Amateur rocket motor casings almost always use millimeters. The diameter of the outer circle is the diameter of the case, and the diameter of the inner circle will be the inner diameter of the case. To make this happen, we'll need to dimension the inner circle to a diameter of 50 millimeters, and the outer circle to a diameter of 40 millimeters. 54 millimeters. Since that's really small now, we'll use the box zoom tool to drag a box around our circle until it's in view. Now that that's done, go back to the Modeling tab. Then we need to extrude the sketch by 480 millimeters. Click Apply for the geometry, and then type in 480 and hit Enter. Then Generate by hitting F5. Now we still need to create the ring at one end of the case. This ring right here. The easiest end to do this at is the one that's still at the origin. Click the New Sketch button, then draw a circle at the origin and specify its diameter. The inside diameter of the ring is 30 millimeters, so we'll dimension it to be 30 millimeters. Next, draw another circle centered at the origin, but this time, wait until the inside circle is highlighted, because we want this circle to be exactly the same as the one on the inside of the other sketch. That wasn't quite it, so I'll delete that. There we go, that's deleted now. There. Now we'll go back to the Modeling tab and extrude that by 5 millimeters. And there we go, there's our ring. Take a look at the finished product, then close Design Modeler. Before we cut to the next segment, pause the video and launch the model step. For this simulation, I'll go into meshing in more detail. If you try and generate the mesh right away, the mesher will definitely get stuck and probably use up all of your RAM and crash the program. This is because it can't handle sharp edges very well. To fix that, we need to put some constraints on how many elements can be in a particular piece of geometry. We do this by sizing the geometry. Right-click on Mesh, hover over Insert, and click Sizing. Click Edge on the toolbar, and then Control-click both outer edges of the cylinder. There's one, and we'll do the one on the other end too. Notice that they are both highlighted. Click Apply in the geometry, and it should say 2 edges. Next, click on the Type box, go to the menu, and select Number of Divisions. Type in 85 in the box below Type that says Number of Divisions, now that we changed it. Hit Enter, and doing that tells the mesher that it needs to have 85 elements around the edge of those circles. Let's do the same sizing for the inside diameter edges of the main cylinder, and we'll do a sizing with 40 elements for the ring. Once again, right-click Mesh, go to Insert, select Sizing. Edge is already selected because we did it the last time. You might want to zoom in a little to make this easier. Then hold down Control and click the 2 edges that you want to size. Click Apply. Change it to Number of Divisions. Type in 85 again, hit Enter. Now let's do the ring. Once again, insert a sizing, edge is already selected. For this, we'll go around to the other edge of the ring. We'll use the Pan tool to drag without rotating. And we'll zoom in more. Go back to Select. Single Select is what we want. Then hold down Control, click those 2 edges this time. Hit Apply. Select Number of Divisions, and type in 40 this time. Now we've got those edge sizings done, let's size the inside of the case. For this, we need a face sizing. Go to Insert, Sizing, select Face, and then click the inner face of the casing. Click Apply, go to the Element Size box, and for our simulation, we'll do 7.5 little e negative 3. This gives us 7.5 times 10 to the negative 3 meters per size per element, or 7.5 millimeters. Now we're done with the mesh. That ends this segment. I will see you in setup. One thing I forgot to do in the last segment was generate the mesh, so we'll go ahead and select the mesh, right click, and then hitting update or generate will work. Either one's fine. Mesh is face by face, and once it's done, you should have something like this. Now in setup, we'll apply a fixed support to the top end of the bar, a temperature distribution that decreases with distance from the center of the cylinder, and a force acting upward equal to the thrust. We'll also add a pressure. To start, insert a fixed support at the top of the cylinder. Right-click Static Structural, hover over Insert, click Fixed Support, and click the top face of the cylinder ring combination. Click Apply. Now we're done with that fixed support. Now let's insert a force on the inner edge of the ring. Go through the same process, but click Force this time. Then click the inside edge of the ring, inside face of the ring, excuse me. Click Apply. And our magnitude is 800 newtons, so we'll type in 800, click Enter, and now we're done with the force. Oh, excuse me, we're not quite done with the force. Notice it's going this way. That is not what we want. So click the direction box, then click this other arrow here. That will change the direction. And click Apply. Now we're done with the force. Now let's add a pressure inside the case. We insert a pressure of 1 kilopascal. That's 1,000 pascals on the inside of the case, which is the face I just selected. Click Apply for the geometry, then type in 1,000, hit Enter. Now we're done with the pressure. Now let's specify the temperature distribution. Before we start, notice that the temperature, as specified in the problem, is a function of radial distance r from the axis, from the length axis. In this case, it's the y-axis. Now this doesn't work very well in the standard Cartesian coordinate system because r squared equals x squared plus y squared. You can't specify temperature as a function of more than one independent variable in setup. So to fix that problem, we need a cylindrical coordinate system. Find coordinate systems in the outline. It's located between geometry and mesh. Expand it to find global coordinate system. That's the standard coordinate system that ANSYS uses. To insert another coordinate system, right-click Coordinate Systems, go to Insert, and select the only option, which is Coordinate System. Select your new coordinate system. It should already be selected if you haven't done anything else. And change the type from Cartesian to cylindrical. For geometry, select the top face. We'll first select geometry, then select the top face of the ring, and click Apply. Then go to Orientation about the principal axis box. The Define By box needs to be set so that the curved line here travels along this face. It's traveling perpendicular to that face right now. Choosing the global z-axis direction should accomplish this. And as you can see, it has. That's it for our new coordinate system. So now that that's defined, we need to insert the thermal condition. Right-click Static Structural, go to Insert, click Thermal Condition. Click the body for the geometry, then hit Apply. Next, go to the Magnitude box, select it, then select Function from the menu. Type in 40, asterisk, left parenthesis, little x, right parenthesis, caret, -1, /2. That's 40 over the square root of x. Hit enter, and a coordinate system box will pop up because you just typed in the variable. You need to know which coordinate system that variable is from. Select that box and then select your coordinate system. You should have a temperature distribution, something like this, once you're done. Now that we're done with the setup, right-click Solution, go to Insert, Probe, and then a Force Reaction. We want to insert that as a body. Actually, you just need to select Fixed Support. Now that that's done, insert a strain tool, equivalent strain, and then insert an equivalent stress tool. Now that all that's done, right-click Static Structural and start the solving process. We'll wait until that's done. Now once that's done, let's analyze the results. Select equivalent elastic strain, and then click the axis that runs along the length of your casing. It should be Y if you set up the geometry right. Click it, it'll zoom to match that axis. You'll be looking along that axis, and as you can see, we're looking at the bottom. Now go to the result box and select 0, undeformed. Then select 1.0, true scale. Notice how the casing changed in diameter, and that's as a result of the stress and strain. Well, really, it's a result of the pressure, force, and temperature distribution, but those go through stress and strain, so that's what happened. So the diameter changed just a little bit, and that's what the casing would look like in real life under these temperature conditions. Do this on your own screen. It'll be the same size. It won't be bigger or smaller. Even a minute thermal expansion can affect the surrounding rocket structure. And it could definitely make it harder to extract the motor grains after a launch, something you'll find out at our practice launches and the Midwest competition. Now explore this deformation from some different directions to get a sense of how the motor casing will deform under these conditions. Notice how it increases in both length and diameter. Finally, check the force reaction. It should be exactly equal to 800 newtons because of Newton's third law. As a bit of a further exploration, the yield stress for this steel is about 250 times 10 to the 6 pascals. What's the maximum stress? Find out by selecting the stress tool, which I just did, and checking the maximum in the scale. Notice how it's much, much greater than that, than 250 times 10 to the 6 pascals, which means it well exceeds the value of that yield stress. So any deformation in this case will be permanent because that's how yield stress is defined. Think about ways to reduce this stress value. Remembering the definitions of stress and strain from the last video will help you out. With that, this video is just about done. Next week I might do a structural simulation for a different part of the rocket, or I might get started on a fluid simulation. I'm Kyle, and for Simulation Team, I will see you guys next time.